Welcome to this lecture on parasitology. Today, we are going to explore the fascinating and sometimes unsettling world of ticks and mites. Imagine walking through a beautiful, tall, grassy field on a warm summer day, completely unaware that tiny, silent hitchhikers are waiting on the tips of the grass blades. These little creatures are like miniature vampires, waiting for a warm-blooded host to brush past so they can grab on and get a free meal. By the end of this session, you will understand their biology, their impact on human health, and the mathematics behind how they spread and multiply. Now that we have introduced our topic, let us look at what makes these creatures so unique. Ticks and mites are some of the most successful parasites on Earth. They do not hunt like predators. Instead, they use a strategy of waiting in environments like tall grass for a host to simply walk by. Some of these parasites are so incredibly small that you cannot even see them without a microscope. Others, however, can swell up like tiny balloons after they feed on your blood. Understanding them is like learning the secret tactics of a tiny, invisible army that lives right in our backyards, our beds, and sometimes even directly on our skin. Building on that intuitive picture, let us define exactly what these creatures are biologically. In the scientific world of parasitology, ticks and mites are classified as arthropods, specifically belonging to the arachnid subclass called Acari. This means they are actually cousins to spiders and scorpions, possessing 8 legs as adults and lacking wings or antennae. Ticks are generally macroscopic, meaning you can easily see them with the naked eye. They are strictly blood-sucking ectoparasites that feed on mammals, birds, and sometimes reptiles. Unlike some parasites that stay forever, ticks are primarily temporary visitors that drop off their host after finishing a blood meal. While ticks are temporary macroscopic visitors, mites have a very different biological strategy. Mites are mostly microscopic and have a much wider variety of lifestyles and feeding habits. Instead of just drinking blood, some mites feed on dead skin cells, others survive on plant juices, and some even burrow directly into the living skin of their hosts. Because of their tiny size and specialized diets, many parasitic mites do not just visit for a meal. They spend their entire life cycle on a single host. This permanent residency makes them incredibly persistent and sometimes very difficult to get rid of once an infestation begins. Knowing their biology naturally leads us to ask why we study them so closely in university parasitology. The reality is that ticks and mites are incredibly important because they are major vectors, meaning they transmit dangerous diseases to humans and animals. Ticks are responsible for spreading severe illnesses like Lyme disease and tick-borne encephalitis, which can cause lifelong neurological damage. Mites cause direct harm through conditions like scabies, where they burrow into human skin, causing intense itching, and they are a leading cause of severe indoor allergies. If we did not understand their biology, we would have no way to develop treatments or public health strategies to protect ourselves. Now that we understand their medical impact, let us look at how a mite infestation, like scabies, can quickly get out of control mathematically. Because mites reproduce continuously and have abundant resources on a human host, their population grows exponentially over time if left untreated. In this formula, N of T represents the total number of mites present on the host at a specific time. N0 stands for the initial number of mites that first infected the host. The constant E is the base of the natural logarithm, modeling continuous growth. The variable R represents the intrinsic growth rate, depending on how fast they reproduce. Finally, T is the time elapsed. If the growth rate increases, the population explodes much faster. Before we move on, let us see this exponential growth with a concrete example. A patient is initially infected with 5 female scabies mites. Under optimal conditions, this population has a continuous growth rate of 0.1 per day. The patient does not seek treatment for 30 days. We plug our known values into the exponential growth equation. Multiplying the growth rate by the time gives us an exponent of 3. Evaluating e to the power of 3 gives a growth factor of approximately 20.085. Multiplying this by our initial population of 5 gives us roughly 100. This physically means that after just 1 month, the patient has about 100 mites actively burrowing in their skin, showing why early treatment is critical. Now that we have modeled mite populations, let us shift our focus to the medical concern of ticks transmitting diseases. We can calculate the probability of a human contracting a disease after being bitten by multiple ticks using the mathematical rules of independent probability. In this formula, P total represents the overall probability that the host will contract the disease after all the tick bites have occurred. The variable P is the probability that a single tick bite transmits the disease, which depends on the local infected tick population. The variable N represents the total number of tick bites the person receives. As the number of bites increases, the overall probability rapidly approaches 1, meaning infection becomes almost certain. Let us apply this transmission formula to a real-world scenario. A hiker walks through a forest where the probability that any single tick transmits Lyme disease is 0.2, or 20%. The hiker finds 4 ticks attached to their skin. We substitute the single bite risk of 0.2 and the 4 bites into our equation. First, we subtract 0.2 from 1, giving us 0.8, which is the chance of escaping infection from a single bite. Raising 0.8 to the power of 4 gives 0.4096. Subtracting this from 1 yields 0.5904. This means being bitten by 4 ticks nearly triples the overall risk to 59%. Now that we have used this probability formula, let us understand where it comes from by deriving it step by step. We start by defining our base case. Let P be the probability that a single tick bite transmits the disease. In probability theory, the sum of all possible outcomes must equal 1. Therefore, the probability of the opposite event, which is not getting infected from that single bite, must be exactly 1 minus P. This represents a lucky escape. We also must assume that each tick bite is an independent event, meaning one tick biting you does not change the probability of the next tick carrying the disease. This sets up the foundation for looking at multiple bites. Continuing our derivation, we now scale up from a single bite to multiple bites. Since the bites are independent events, we find the probability of escaping infection from all n bites by multiplying the single escape probability by itself n times. This gives us the term 1 minus p, all raised to the power of n. However, doctors do not just want to know the chance of escaping, they want to know the risk of getting sick. The chance of getting infected at least once is the exact mathematical complement of escaping every time. So we subtract our escape probability from 1. This perfectly yields our final formula, proving how multiple small risks compound into a massive overall threat. So we have proven how their risks compound mathematically. This brings us to a visual comparison of their biology. On the left side of this diagram, you can see the tick life cycle. Notice how it progresses from an egg to a six-legged larva, then to an eight-legged nymph, and finally an adult that attaches to a mammalian host for a blood meal. On the right side, we see the microscopic world of the scabies mite. Look closely at the cross-section of the skin. The mite is actively burrowing through the stratum corneum and epidermis, leaving a trail of eggs in its wake. This visual perfectly illustrates why ticks are temporary vectors, while mites create persistent, localized infestations. We have covered a lot of ground today, so let us review the key takeaways. First, ticks and mites are highly specialized arachnid parasites that have a profound impact on global health. Remember that ticks are generally larger, temporary blood feeders, famous for transmitting severe systemic diseases, whereas mites are often microscopic, causing localized skin conditions like scabies. We also learned how to apply mathematics to biology. Mite populations grow exponentially if left untreated, and the risk of contracting a disease from ticks compounds rapidly with every additional bite. Mastering these concepts gives you the foundational knowledge needed to diagnose, treat, and prevent some of the most impactful parasitic infections in the world.